Another important setting in which you'll find yourself doing integrations, at least in physics, is with work, okay, computing work. Now, what is work? It's the integral of the force times the displacement, okay? And we do this integration because the force that you apply on an object to move it from point x equals a to point x equals b might vary, okay? So one very common example of a force that varies as it's moving is an object connected to a spring. So if we want to find the work required to stretch a spring from x equals a to x equals b, and this spring obeys Hooke's law, then the force that the spring applies is negative kx, where k is the spring constant, okay, the spring constant or the force constant. And what this is telling you is that the more stretched or compressed a spring is, the greater the force. And so the force is varying, and we do have to take an integral. So the work is equal to force times the dx. We plug in negative F spring. Why do we plug in negative? Well, if the spring is applying negative kx as a force, and we're trying to stretch it, we're going to apply an opposite force to the spring. And so that's where that minus sign is coming from. And so we get kx dx there, and we integrate from a to b, and we end up with that antiderivative there. Okay, and so that's the work that's required to stretch a spring from x equals a to x equals b. Another setting where you'll run into integrations is calculating the work required to lift the object. Okay, so suppose you have this one-dimensional object. It could be a string, for example, and you want to lift this string up. Okay, you want to lift this string up. Well, how do you do that? You have that in general, to take an object of mass m and lift it a distance y, you have that it's mgy. Okay, the force mg is that of gravity, and we lift it up y, and so we do the work mgy there. Okay, well, to lift up this small piece of this string dm, okay, we're gonna use this linear density. Okay, this rho is the line density, it's linear density, and so the mass of that little piece there is that linear density times the length of that little piece there, dy. And so the work required to lift just that little piece there is the mass times gravity times the distance that you're lifting it. You're lifting it L minus y distance. Okay, you could see that you have to do more work to get the bottom part up than the top part. Okay, you have to do no work at all to get that top part. It's already up there. And so that's why we have to do an integral, because we have to add infinitely many pieces that we're lifting up. And so dm is going to be rho dy, and so we get that formula there, and then we just integrate. We add all the works that we need to lift all the tiny pieces. And so we end up with this formula here. Okay, L is the length of the string. Okay, you could see here's y equals 0, and here's y equals L. So let's take a look at an example. A 10-meter chain with density 1.5 kilograms per meter, okay, so that's a linear density, hangs from a platform at a construction site that is 11 meters above the ground. Compute the work required to lift the chain to the platform. Okay, so for this problem, we're going to set our y equals 0, not at the very bottom, okay, where the actual construction site is 11 meters above the ground. So we're not going to set it to the ground. We're just going to set our y equals 0 at the bottom of the chain. Okay, so be careful about that point. I mean, this can work if you set it at the ground, but you're going to have to shift your bounds of integration. So here's the formula. And again, y equals 0 is at the bottom of the object that we're lifting. And so we have our rho is 1.5 kilograms per meter. Our g is 9.8. It's just a constant, 9.8 meters per second squared. And 10 minus y is the length is 10, and so we're getting 10 there. It's a straightforward computation, and we get a work of 735. And since we are using standard units, this should be joules there, but this is a math class and we're not paying too much attention to the units. Another application is with pumping problems. Okay. With pumping problems, we want to pump out a bunch of, say, liquid out of an object, right? Out of a, say, tank or something. And again, we first take a look at the dW, the work required to just pull out this slice. Okay, we're going to just take a slice of that liquid or whatever it is, maybe it's water. And to do that, here's the cross-sectional area. It's A at Y, at a depth of Y. Okay, A at a depth of Y. That's going to have a mass what? Its mass is going to be the cross-sectional area times the height dy of that little slice, okay? Dy of that little slice, and so that's what you're seeing there, times rho. Okay, what is rho here? It's the volume density. So rho is, in standard units, kilograms per meter cubed. So dmg, okay, so mass times g, that's the force again. And so you have to apply opposite force to pull it up, than the force of gravity. And dy is the distance you pull up that slice. And so if this is at a height of h and at the very bottom is a height of 0, or a, let's say, and the very top is at a height of h, so you want to pull up this slice to the height of h. Well, then you're going to pull it up a distance h minus y. Okay, this is the distance that you pull it up. You're going to keep pulling up slices from a slice at y equals a to a slice at y equals b. Okay, and so you have that general formula there. So let's take a look at an example. A cylindrical tank with a length of 10 meters and a radius of 5 meters. So the length of this, if it's pulling back here, you could imagine it is 10 meters. And a radius of 5 meters, so that's just, that radius there, is on its side and half full of gasoline. Okay, that's where that half full is coming from. How much work is required to empty the tank through an outlet pipe at the top of the tank? So the top is going to be up here. The density of gasoline is 737 kilograms per meter cubed. Well, the first thing we need is the cross-sectional area, right? AY. So we have a width. The width here is going to be 2 times x, which, because this is a circle, okay, this could be described as x is equal to 25 minus y squared. And where's that 25 coming from? Because the radius is 5. Okay? And so that could be described, in fact, this whole side hemisphere here is this x is equal to positive 25 minus y squared. Okay? And so we're going to get a width of 2 of that because, we have one x here and then another x there. So that's where that 2x is coming from. And what about that 10? Well, this thing has a length of 10. So this actually extends out. If we imagine drawing this, it'll extend out 10 meters. Okay? And so that's where that 10 is coming from. And so that's the cross-sectional area of one slice that extends out also. Okay? It's going to be the width, and the width depends, right? At y equals 0, you get a very wide slice, and at y equals negative 5, you get the slice is 0 in width. But they all have a length of 10. Now, what about the dy? How much are you pumping this up? Okay, you have to pump it up a distance 5. That's 5 there. minus y. Okay, and this works for negative values. So if this was here, for example, -3, then 5 minus -3 is 8. And so yes, you are lifting it 8 above. Okay, and so that's our general formula there, h minus y. It still works here. That height is at 5, and we just have the minus y, and it still works. Okay, that formula still works. But we have to be careful about what our a and b is, because we're integrating now from a equals -5 to b equals 0. Okay, so that's because it's half full. The tank is half full, and so that's why we're going only from 0 to 5. Okay, and we're still lifting 5 minus y. And just plugging all of that in, we just plug in the values for rho, g. Here's that 20 there, and we just do a straightforward computation there. We do a u substitution and integrate, and we get that value there for the work. And so this is how you do these kind of pumping problems with the general formula. Sometimes you might have to modify, the formula a little bit, but this should work in almost all cases. So the game plan is straightforward. Get that cross-sectional area. That's generally the hardest part. Make sure that your the distance that you pull a slice is consistent with the formula above, and then carry out the integrations. Make sure that this is smaller than that, and it is. -5 is smaller than 0, and all these problems should work out for you.